instance, fairly annoying, appear in 10-star movie reviews and 1-star and so on. And so, for instance, fairly annoying appears mostly, fairly kind of attenuates the annoyingness of something, and so it appears mostly in 4- and 5-star reviews, but it's relatively flat. And what we show here are two curves, which are basically the predictions of how often our model thinks a bigram would appear in a certain category. And in many cases, both the recursive neural networks and the matrix vector recursive neural networks give similar predictions, but there's some cases where it's clear the operator really modifies the sentiment distribution that you would assume. And so in the case, for instance, for not annoying, the matrix vector RNN gets sort of the positivity of annoying and really changes it and makes it much flatter. Whereas the RNN is actually not able to do that and gives it, also still a very negative distribution. And here on each row we actually have the same adverb, and in each column we have the same adjective. And so you really see that the matrix vector RNN can modify these distributions. And so not awesome, for instance, where unbelievably awesome is, occurs very often in positive movie reviews. Not awesome really doesn't. And the matrix vector RNN can sort of capture these logical operations, but also they go beyond logical operations. And compositionality that when you have, for instance, on the lambda calculus in very clear sort of logical terms, it cannot capture some of these kind of fine sentiment compositionality phenomena. And another interesting one that actually both models get right is unbelievably sad. And in the interest of time, I won't ask, but basically the interesting question of why do you have this U-shaped curve here that both models can accurately predict? And the main reason is that, one, people like really unbelievably sad movies. And so, you see this diagram a lot in very positive movie reviews. But if you think the performance of actors was unbelievably sad, then you get more to the pathetic kind of thing. All right. Lastly, this is the last slide. These matrix vector RNNs can also be used for relation classification, where again we take this tree structure and now you can have a path, a syntactic path between two words, and then classify based on sort of the vector representation that was at the top of the path in between these two words. And this kind of model gets state-of-the-art performance on the semi-valid task from 2010 and outperforms a lot of others. All right, so I hope I could show you that recursive deep learning, which is really like the sub-community of the sub-community of deep learning, can predict hierarchical structures really accurately and classify sort of structured outputs using these compositional vector representations. And I think there's sort of some controversy of like, well, how should we apply deep learning compared to like to NLP, compared to vision, for instance, which starts with sort of just pixels and you learn, immediately you learn useful features as you go up in hierarchy. And in NLP, we already start with useful representation, like words already make sense, unlike pixels. But one of the interesting ways, I think, of applying deep learning is to sort of learn these compositional vector representations that try to describe more and more of the content. We already get, after working for a very short time on this, already state-of-the-art performance in sentiment analysis, paraphrase detection, relation classification, and we can actually apply these same ideas to vision. And now I'll hand over back to Joshua for part. Thanks, Richard.
So in the last part of this tutorial, we'll cover a number of subjects, more applications, in particular neural language models, and some pointers to resources, reading code, and then something I think several of you are interested in if you want to actually apply these things, recommendations, tricks, how to train these things. We won't have time to go into all the details, but I'll give you some basics and some pointers, and then a little bit of discussion. So here's a list of existing applications of deep learning in NLP. 10 years ago, someone would ask me, how many applications of deep learning you think would happen in NLP? I really wouldn't have thought about so many. So For language modeling, we're going to talk about particular applied to speech recognition and machine translation, acoustic modeling. We've already talked about part-of-speech tagging, name entity recognition. The same models have been applied to trunking and semantic or labeling. We've talked about parsing. There are other applications of deep learning for parsing. We've talked about some sentiment analysis. We'll talk a bit more about that. We've talked about paraphrasing. And I'll say a few words about question answering and word sense integration. So let's start with sort of the grandparents of all of these. The neural language model, we've already talked about the structure. The idea is that it turns out we can model the probability of a sequence of words by modeling the probability of the next word given the previous word. If we're not able to compute that probability exactly, there are some approximations that make sense to model the distribution of words. And once you have good models, especially if you have probabilities, you can apply them quite directly to speech, translation, and compression. I don't have time to talk about compression, but it should be pretty obvious that if you can represent these probabilities accurately, then you can compress text efficiently. And there's one point I'll talk about, which is that a computational bottleneck. When you do these, you build these models, you're trying to predict the next word, and each those words are taken in a large vocabulary, like 100,000 or maybe even a million. And so the amount of computation just to make your prediction is going to scale linearly with the size of the vocabulary, and that can be quite expensive. But fortunately, in the last few years, there have been several heuristics and techniques that have been proposed to deal with that are very efficient. I'll say a few words about that. So this whole story of neural language models started about 12 years ago. I published this paper at NIPS 2000 called a Neural Probabilistic Language Model, and we've already seen the architecture. One of the basic ideas I had in those days was that by mapping words to a continuous space and then taking the representation at that level, so we have the one-hot encodings or the symbols here. We map the sequence of symbols to a long vector, which is the concatenation of the word embeddings, and that's kind of continuous representation. Then we have a smooth mapping that goes into probability for the next word. And because this is smooth, it means that we can get some generalization, automatic generalization, so that if words have similar representations, then the function from here to here is going to produce similar outputs. And that's a very important kind of generalization. So one of the modern examples of successful application of these ideas generalizes the kind of models. So it's another picture for the same kind of models where we have a window of inputs, and then hidden units, and then we predict the next word in the vocabulary. You can generalize that by using so-called recurrent networks. We haven't touched much on them, but they're an interesting variation that can represent longer context than the fixed window. In fact, arbitrarily long context in principle. But we're believed to be hard to train. In fact, I worked on this, and I'll say a few words about that. Nikolov and his collaborators, who've already mentioned their results, showed that you can not only get perplexity of language models to go down substantially, like from 140 to 102 on this broadcast news data set, but you also get word error rate on the speech recognition problem to decrease. So in this graph, the green bar here represents the performance of SNA4 programs, and the other ones here represent different variants of his recurrent neural network model. And you can see they do substantially better, going from like 13 point something to 12 point something. But the interesting thing here is that the x-axis here is the size of the model. And basically the bigger the better, at least in these experiments. Of course, these are done with large quantities of data, but this is something we observe very often in deep learning, which is bigger models tend to do better, especially in those situations where you have lots of data, which is often the case in NLP and vision problems. And part of the reason is we're doing all of this unsupervised learning which essentially prevents those models from overfitting. Now, let's come back to this issue of the computational bottleneck. We're trying to predict one word out of a large number, and that's expensive. So one of the first ideas around that was proposed by Ulrich Fenk, and what he does is, instead of predicting all the words, he only predicts the most frequent words, that we call a short list, and then uses an n-gram for the others. So that's one trick. But I think, and there's been other tricks. For example, we've seen the trick of contrastive training, where we just randomly sample negative examples, but it doesn't give us probabilities. There's another trick which allows us to keep probabilities, which is the use of a hierarchy of classes for words. So the idea is, instead of predicting words given the context directly, we're going to predict word categories given the context. And then, given the word categories, we're going to predict words within the category. So at each level, the number of things we have to predict, that we have to distinguish, is small. For example, here, if we only have two levels, so words in their categories, instead of having order of n computation, where n is the size of the vocabulary, we can do order of the square root of n computation. Assuming we have square root of n categories and square root of n words in each category. And instead of having two levels, you can have three levels, or a whole binary tree, and in that case, the amount of computation goes from order of n to order of log n. So you can really get rid of the problem using this idea. But in fact, just putting two levels with square root of n is typically sufficient, because you would go from, say, 100,000 to 300, being the square root of 100,000. So 300 is not any more a bottleneck, because it's comparable to the computation you do in human units. And in fact, you can choose the categories in pretty arbitrary ways, and it still works. Although some people are trying to improve and be smart about how to design these categories, the basic idea is there and works quite well. So there were initial applications of the language models in speech recognition, again by Schwenk here in this journal paper, where he shows perplexities going down, like from 50 to 45, and word errors going down. So in this graph, the hybrid, the blue and the green, represent the models using his neural language model, and the other colors represent using only the backup models. And not only you can see performance always increasing for different systems, but as you add more training data, the advantage does not vanish. So several people have admitted the opinion that, well, we just need to have more data, and we can build bigger n-gram models. And if you're Google, you have tons and tons of data. You can just build bigger non-parametric models. And then there's no advantage to having smaller, more complicated models. But actually, it's not true. And even with large quantities of data, the advantage of these richer models that have internal representations and abstraction seems to be important. Another kind of applications of language models is statistical machine translation. So it's the same kind of idea. We just exploit a better language model. And so again, Schwenk presented recent results on Arabic English bytexts, where perplexity went down from 71 to 57. Now, the interesting thing is not only that perplexity went down, but the size of the models is also much smaller. So the backup model was huge, like 6 gigabytes, and his neural language model was about 500 meg in terms of memory. And of course, the important part is that the blue score, the actual translation task, improved by a substantial amount here, 1.8 blue score improvement. So let's see more applications besides language modeling. We've already seen how the kinds of models that Richard has presented could help to model the semantic aspects, not only of individual words, but of sequences of words. So last year and this year, people with whom I've been working have proposed related approaches to modeling semantics, where we focus on a very sort of simple point of view, which is a lot of semantics can be summarized by relations. So we often have phrases that have essentially a relation type, like a verb, and then arguments like $1, $2. And for example, databases are organized also as relations, where you have a relation type, and then arguments like a particular object and another object. And so what we can do is build models that take the identity of the relation type and the relation arguments and output a score, which you can understand as a normalized law probability or something like that, which you want to be large for plausible things and small for implausible things. So we considered variants of these ideas with different kinds of architectures. In the paper last year, we did something related to what Richard has talked about, using matrices to operate on the vector representation. So the idea is that each word, like the left-hand side, is associated to a word embedding. But what we would like to do is change that embedding, depending on the relation, to map it to a new space. So each relation has as parameter a matrix that's going to operate on the embedding of the right-hand side, and another matrix that operates on the embedding of the right-hand side. So we've done that and it works well. But one thing that is not satisfying with this model is that relations as object types have a different status as left-hand side and right-hand side. Whereas if you want to have relations on relations, you'd like relations and nouns and verbs and everything to be in the same space, so that you can have relations on relations. So in this more recent model, every object, every relation, every noun lives as a point in the vector space. And in order to achieve the similar effect of doing an operation on the representation, we basically train an NLP, which takes two arguments, the embedding of the left-hand side and the embedding of the relation, and outputs a modified embedding. Then we do that for the left-hand side and the right-hand side, and then have some score, which might be something like L1 distance or dot product. The other novelty is that instead of having a single word for the left-hand side, we can have a whole phrase. And we use a semantic role labeling from Colbert to split the sentences into subject phrase, verb phrase, and object phrase. And finally, in addition to having embeddings for individual words, we also have embeddings for different senses of the word. And we'll see how we can take advantage of that. So one thing you can do with these kinds of models is question answering. Because what the model does is given a left-hand side relation and the right-hand side outputs a score. So what you can do is you give it a left-hand side, you give it a relation, and then you try different possible right-hand side, and you see which one gives the highest score. And you just pick the one with the highest score, and that gives you a plausible right-hand side to match this left-hand side and relation. So if you do army, attack, well, then plausible answers to this question would be troop, armed service, ship, and so on. You can do the same thing for any part of the triplet. So for example, if I give you the verb and the object, you can find a good subject that is going to match these. So you can use that to actually add relations to a database like Freebase or WordNet. And you can use that to create so-called meaning representations. In other words, going from text to structured triplets that describe the semantic of the phrase or of the sentence. You can also try to understand what the embeddings do by looking at nearest neighbors. Remember that both words and their senses, like here _3 is a sense number 3 of print, live in the same space. So I can ask the question, what are the words and senses that are close to the word mark? Or what are the words and senses that are close to the sense 1 of mark? And I can see here that for sense 1 and sense 2, I end up in a different region in my space of words and senses. Here, this is a sense which is like a score, number, relation, evaluation, whereas this one is near marking, symbolizing, naming, punctuation, and so on. Now, since we have different embeddings for senses, we can use this also for word senses integration. The way we do that is very simple. It's similar to this thing, but instead of considering here all of the possible words and senses to fill an answer, we assume we know what the word is, but we don't know which of the senses is appropriate. So we just score for all of the possible senses of a word, and we see which one gets the highest score in the context of the other words. And so we can do word senses integration. However, we can only do it here on sentences that have a subject-verb-object structure, because this is how our model is trained. So if we apply this on sentences from sense level 3 which have a structure, we beat the state of the art and other methods we have compared with. And we can apply the same techniques on other word senses integration data, like the extended word net, and again, get good results. So this idea of having multiple embeddings for different senses of a word, as been explored by other authors. In our case, we've sort of used the list of senses that was given in WordNet, but we can also discover